Hey guys, welcome to a surprise stream for Ferris Makes Emulators. Um, from the last time that I streamed, I was playing with we just started getting the sound stuff working in the Virtual Boy emulator, which is pretty cool. But we didn't actually get that far. We got to sort of memory mapping some of those registers, and we didn't get much farther than that. And after doing that stream, I couldn't really get out of my head. I tried yesterday, just in the weekend, to start coding on other bits of the emulator, and ended up just wanting to work on the audio stuff instead. I couldn't really help myself. So I ended up starting on that, and I actually made a ton of progress fairly quickly and figured out a ton of this stuff that actually ends up being really simple, or at least a lot simpler than I thought it would be. So I wanted to have a quick stream and just share some of this stuff before I got too much further. So, by the way, I'm not getting any of the chat or my view count, so if you guys want to ping me in there and let me know you're live, that'd be helpful. Daniel Collin, how's it going? There's one. Maybe it is working. Cool. Anyway, so where we left off in the last one is we were doing some memory mapping. So we had voice 1 through 4 stuff being mapped, or voice 1 through 4 at that time. So this shouldn't look any different. Things I've added since then, of course, is mapping addresses for the 5th voice, but currently it's actually missing a couple things because the 5th voice also has some modulation and sweep stuff that I'm not implementing, or that I haven't implemented yet. And then the 6th voice, which is going to be a noise source sound signal. Zaumauk83? Zaumauk? I'm not sure if I'm saying that right. How's it going? Dan Collins says he was tired and was up watching the Super Mario AGDQ race last night. Yeah, totally. I was as well. That was pretty fun. Reshurum, nice. First time catching one of these live. Awesome. Good to have you. So anyway, so I added this other mapping, really straightforward. In the module here, though, I did quite a lot of stuff. So Malk83, I believe. Again, I'm sorry if I'm saying that wrong. Thanks for the follow. Also, if that following noise is kind of annoying this time, I apologize. I need it so that I can hear that people actually followed and I can thank them for it. I think that's really helpful. Normally, I don't have my system audio in the stream, but this time I do because we're going to be hearing some audio stuff. So yeah, sorry if that's annoying, but we're just going to deal with it this time. Zama UK 83 says, okay, that's much much easier for me. I always lose this. First time viewing this live as well. Cool. Good to have you, man. So if we go to the memory mapping section of this, just to kind of dive in somewhere, I think I left off just mapping a bunch of these registers. We had the wavetable stuff set up, and we were just mapping voice registers to the actual voice structs. Again, adding the other voices to that is absolutely trivial because it just goes through these voices. I always lose this. Thanks for the follow. For Right Byte, I don't think I had any of these implemented except the wavetable stuff, which basically hasn't changed, except I fixed a bug in there, and I'll get to that in a minute. Of course, I mapped all the other things. I don't think anything has changed really there, but a lot of other things have changed. In particular, the voice structs themselves. I want to go over kind of how those look now. So I ended up splitting things up a bunch because initially I was going to start with just having a voice struct, and then we kind of talk to those. The problem is that there's different kinds of voices, and a lot of the voice code ends up being the same, but a lot of it, or the sort of key parts for the actual sound sources, ends up being different, particularly because we have what's called a standard voice in some of the documentation. And that's just going to be something that's reading at a waveform memory and producing sound that way. I also figured out a bunch of stuff about the waveform memory format, which makes that a lot simpler and makes all the math we were doing last time make sense. I'll get to that. But then we also have currently a noise voice, which is, again, that last voice. And that, to a large degree, is the same. It still has the same play control and volume stuff. and the same envelope, but the way it actually generates sound and the clock frequency at which it generates sound is a little bit different. So I wanted to split things up. So instead of just having like voice, we now have like standard voice and noise voice. We also have this voice trait, which can allow you to get play control register, volume register, and envelope from that, and that's used later in the mixing stuff. And of course, the different voice types will implement that. You'll notice there's no actual output here, and that's because the different voices will actually generate output differently. Or like some of them need different kind of dependencies, and yeah, I'll show you that in a sec. No Goma 314, thanks for the follow. Basically though, I just ended up splitting up a bunch of stuff. Like before I had, like here we have the frequency low and high just in the struct here. We had the same thing with like play control and envelope as well, and I just ended up splitting those out into their own structs here. You can see I did that with the volume register as well. And that's because all these voices had that same kind of register and the same kind of backing store, and I haven't actually really implemented that beyond just like setting the bits that we had last time. So like the envelope isn't really doing anything. The volume registers are actually doing stuff, and I think I'm looking at 1 bit in the play control right now, so it is a bit wrong, but that's all right. But yeah, again, I wanted to split those out so that I could, then compose them back together in the different kind of voices. So instead of having like I considered different ways of fitting these bits together. I considered having each voice contains like a sound source struct, and then have it defer all the actual sound generation to that. But then the actual voice interface still has to be different because some of them have different registers. So I thought that was a leaky abstraction. So I thought it would be better to just split out all the individual components that all the voices have, and then just compose them in different ways for the different voices. And I think that that's a pretty good way to do that, except that there's still the third voice type that I haven't implemented because I'm just treating the fifth voice as one of the other standard voices right now. So that's what you see basically up here. You can see there's the play control register, which just has these like read and write, and then they'll set the same bits that we had in the last one. Same with the volume register, and the envelope is basically the same as that as well, although this actually has some logic missing. This will get a little more complicated as the envelopes actually start, working. Right now it also has this level thing here where you can get the level of the envelope at a given point in time, and right now it just gives you the maximum volume. Because I'm still kind of hacking a lot of this stuff together until I figure out more of the logic. But already this was really useful because, I can play you basically what stuff sounds like before I move on. I know I'm talking a little fast, so if you guys think I'm explaining something poorly or would like me to go into more detail, just let me know. What I'm going to do... Oh, that doesn't work for a second. Here, let me close this. So I'm just going to run the emulator. Right now we're still doing wave dump for the actual audio output. So I just need to run one of these games for a little bit. In particular, this is Galactic Pinball, particularly because I really like the music in this game. It also has some vocal samples at the beginning, which right now don't play, and I don't know if they're, if that's because, well, I guess it's because it uses modulation stuff, because that's one of the only things that I haven't implemented. Other than like the envelope and stuff, but the envelopes just make things sound better. The modulation should actually make this sound like vocals. Right now, we just get some DC offset when that happens. So now I've let it play a little while, I can close this, and we can open up the wave file that this generated, which is just out.wave in the same folder. So I'm going to bring that over into Ableton. And Ableton, at least with my current settings, will warp the sample by default. We don't want that, or else it'll stretch it. But anyway, this is the basic output that I have right now. So it's sort of these ambient, spacey kind of sounds. By the way, also let me know if I need to adjust the volume on my system audio. But then we get kind of a theme with some sound effects. You can see the panning is working. And then this is a DC offset where there's supposed to be a vocal sample. And then we actually have, basically the theme of this song. Just like the title theme of the game. And overall, it works pretty well. It sounds very digital, of course, because I'm only doing, actual digital sound generation. I'm not doing any like post-filtering in the digital audio converter or anything. and not doing any kind of like anti-aliasing or anything, because I don't think the real hardware would. I think it's just going to get some of that stuff for free with post filters, which is just the analog circuitry that comes out of the DAC. But anyway, this is progress, and a lot of it came together way faster than I thought. In particular, the like how you generate frequencies and how those work ended up being really simple once I just kind of thought of this as a bunch of counters and like shift registers and stuff, which is really what it is and totally makes sense because it's, you know, cheap sound hardware from the 90s. So everything kind of fits here. Again, you can see things are pretty blocky. You can also see that everything is above above the middle line here. And that's because basically everything is a DC offset. All the sound is actually generated unsigned. And I guess from some of the documentation I've read and looking at the board, it looks like there's some analog circuitry which will end up filtering a lot of that out, so you can actually get much better levels. But for now, we just get everything offset. It's also a little bit quiet in terms of the actual overall headroom, but that's only for certain games. Some games actually totally use this, and I'm not entirely sure I have the levels quite right, but definitely we're ballpark, so that's really helpful. So basically how some of the sound output stuff works, if we go all the way down, all this is still in one file too, as I'm kind of figuring this out, but I'll end up splitting it up into different modules later. But if we go into this VSU here, which is the actual sound unit itself, we had the kind of standard interfaces for memory mapping. Oh, by the way, another thing I changed is I had this memory mapping stuff in the read and write half-word functions, but I found more documentation suggesting that all of these are only 8 bits wide, and they should actually all be accessed by byte. So I ended up just putting those in the read and write byte methods instead, and then made read and write half-word just mask off some bits of the address and then just read the byte. So that just kind of made a little more sense in my head. But eventually we have this cycles function here. And this is, so in the emulator, we tell the CPU to run X amount of cycles for a given frame currently. In the future, we'll also need the possibility of, like, when we need to produce more audio, which is going to be a little more time critical than video frames, we need to say, hey, run this many cycles that corresponds to that many samples of audio generated. But regardless, it will run a certain amount of CPU cycles, and then the CPU will basically tell all the other hardware that, hey, I ran X cycles. And eventually that gets into here. So like this piece of hardware has this, the video hardware also has the same function. The only real difference, of course, is that this takes in the number of cycles that went by and then an audio driver. And again, an audio driver from last time is just this, basically trait with this output frame function here. And the idea is that whenever the sound hardware ends up producing an audio frame, so when enough cycles have gone by, when enough time has gone by that there should have been an audio frame produced, the audio hardware will just dump the frame here. And a frame is, of course, just a left and right sample pair, which is a common term in audio. So like this unit runs at 41,700 hertz, so that's 41,700 FPS, basically. So there will be that many of these per second. Ideally, I actually also did some math, and I don't actually think that that's a correct number. I think that's a rounded off number, which also can kind of make sense, and I'll get to the logic for that in a second. But basically, all this is going to do is it's going to loop through all the cycles that went by. And it would probably be a little bit faster to do less dispatch here and just say, hey, voice 1, run, X cycles. But the thing is that if like, it simplifies a lot of the logic to just run them on a single cycle clock, or like single cycles like this, and then just if anything happens and we need to mix a new sample, we just always get it on that clock boundary instead of like having to kind of mess with that scheduling. Might be a tiny bit slower, but I'm not going to worry too much about it, not in this case. So for every cycle that the CPU ran, we're just going to tell each of the voices that a cycle happened. And then we have this sample clock counter. And so this is where I kind of get into basically the most common pattern for making this sound hardware work. If you want to divide a clock, so for example, this audio unit runs off of a 20 megahertz clock, and every 47,100 41.7, whatever the numbers are, for our sample rate, whenever, like 41,700 times per second, we want that to produce an audio sample. So we basically have something that runs, that we have a clock that ticks 20 million times a second, and then a clock that we need to tick at our audio sample rate, right? So we need to sort of divide that incoming clock to produce that out, like the audio sample clock, right? And the easiest way to do that is just have a counter. So if we know that we can divide that, 20 million interval clock evenly with our sample rate, then we can basically just have a counter that counts up every CPU cycle. And once it reaches a certain value, it'll reset, and then it will sort of like tick its own clock, if that makes any sense, right? And so I did some back of the paper math, or back of the napkin math, basically. And like, basically I wanted to figure out what this period was, right? So we had again, the 20 megahertz clock, and we need to drop it down to 41,700. And if you do the math, it's actually not evenly divisible. And what this actually suggests to me is actually that the sample rate that's in a lot of the documentation is slightly wrong. We can actually get really close to that. I can show you basically how it works, if I remember the exact details here, but it's pretty simple as far as I know. So the idea is that we have, basically I do most of the timing in nanoseconds. And the reason I do nanoseconds is because if you look at the CPU clock frequency, which is again 20 megahertz, that ends up having a period of 50 nanoseconds. And so I just picked like what is the nearest thousandth unit of seconds that I could use that would cover all the cases. Eventually, I probably want to refactor everything so that everything happens in 50 nanosecond time steps and just count everything, in integral values of that. But since I didn't have a lot of the hardware done, I didn't know if anything else would operate at a different frequency. Turns out it doesn't. Basically, everything runs off of this 20 megahertz clock, so that actually would be appropriate. But it ended up also kind of simplifying the math because I didn't really have to worry too much about like these kind of weirder 50 nanosecond units. I could just worry about nanoseconds. That makes things a little bit easier to handle. But basically, all this clock is going to do is just get, like, for every sample, it has this little clock counter. And it's just going to increment it by how many nanoseconds there were per CPU clock. And once the amount of nanoseconds gets to whatever our sample period is, then we just, again, reset the counter and we say, okay, a sample clock happened. It's like the rising edge of the sample clock. So it ends up being really straightforward, and then we just have to figure out the sample period. Now, if we go to the top, I have the sample period here, which is basically seconds to nanoseconds, which is this how many nanoseconds in a second. So I'm just saying 1 second divided by our sample rate is going to give us the period of the sample clock. And you can also see here I have this little comment here where I was talking about, okay, the math actually doesn't work out to be 41,700 hertz. It works out to be 41,666.66 repeating hertz. And the way I figured that out is I just took like, okay, let's take, I think I just did 20 million, whoops, one less. And I just divided it by 41,700. And you don't get an even number, but you get really close to an even number, right? And that'd be like 480. So if we take 20 million divided by 480 again, so like if we're going to do a counter like this to divide our clock frequency, it basically has to have an even number, and that's why I'm looking for even numbers here. If we divide it by 480, we don't get exactly 41,700, but we get 41,666.66 repeating. And since all like the documentation basically say 41.7 kilohertz, and there are also other areas in the documentation which round up that number, I'm pretty certain that this is correct. And you might be thinking, well, okay, well, it's kind of weird that the sample rate would be a non-integral number, but it actually wouldn't matter in real hardware because it's basically just going to, like, there's no audio buffers or anything that actually deal with these samples later down the line. It's just eventually this changes whether there's voltage on these 8 wires that end up going through, a DAC in real time. So you can really have like any sample rate. We just want one that's, of course, convenient for human ears, which is going to be around, 41,000, 41K or so. So anyway, the point is that this, I'm pretty sure that this is the actual sample rate of the system. And again, we just get that by running a counter at the, higher frequency clock. And we use that to generate a lower frequency clock. And basically, whenever that lower frequency clock happens, we just need to output a sample. So does that make sense to everyone? Because I'm not sure I'm explaining it particularly well, but this ends up being a really common theme, especially in simpler hardware design like this. Basically, whenever you have a higher frequency clock and you need some other lower frequency clock, you'll end up with a counter like this. In this case, I count up by 1 every time, but sometimes you might have a different max value, and you might count up by a different number. And what that kind of allows you to do is it allows you to just say okay, the clock is actually just this 1 bit of the number, and that's probably how this part's actually implemented in hardware. But again, the point is we just need this lower clock from this higher clock. It's about what we expected it to be, and whenever that goes high, in this case, it doesn't actually go high and low, so we can kind of ignore that. But whenever that triggers, we need to output a sample. And the reason why I asked, kind of making sure that I'm explaining that good enough, is because this little concept here is basically it happens a couple other times as well. In particular, the way that the frequency generation stuff works the same way, and yeah, that actually is just repeated twice with different intervals, because there's one frequency generator for the pitch stuff, and there's another frequency generator for the noise stuff. Whew. So if we go back to the code, then we can go back to that counter. And remember, this is just the top level stuff. So at every clock tick, we're going to tell the voices that a cycle happened. And this is again because the the standard voices have one kind of clock that they're all using to basically generate sound at different frequencies, and then the noise clock is generating sound at a different frequency. So we just want to tell it, basically that it will run this many cycles, and they'll have their own counters in here that will have their own little clock ticks. But when we need to generate a sample, we do the sample clock. And here I just put this in its own function just for kind of clarity, because this is basically just dispatching cycles and counting. And then here's where we actually do the logic. In the video hardware, I do this a bunch of times as well, because it also uses this pattern. Here you can see I commented out some of the sound disable stuff, because I'm still working on that register a little bit. We're basically assuming that we always are supposed to generate sound. So in particular, all I do is I make these accumulators for the left and the right sound output for the sample. I call this mix sample function, which takes in those accumulators or references to them, takes in a voice and the voice's output. And I'm a little bit unsure about this pattern, but it ends up working out pretty nicely. And it just literally accumulates those samples. After that, there's that basically just adds a bunch of numbers, and out of that result, we need to mask out some of the bits, convert it to a signed number, and then just output it. So that ends up being really straightforward. We can actually take a look at mixed sample, just because again it's pretty simple, and then we can take a look at the voices themselves. So mixed sample is basically going again to take these accumulators, and it's going to take the voices and what their output would be at this point in time. And this basically, the reason it takes the voice is because the voice has stuff like play control, envelope, and volume, and we need to be able to read those out of the voices. And the reason why we don't just do the voice output here as part of the voice struct here is because, again, the voices may need other dependencies to actually generate that output. For example, the first 5 voices need the wavetables from the audio unit itself to actually generate output, whereas the noise doesn't. So that's a subtle difference. I may actually end up just passing this in as an argument to cycle or something, or maybe all the outputs actually get this, but only these ones use it. But I'm not really sure about that. I don't think that really matters, just some architectural detail. But anyway, to actually get this mix sample, basically has 2 jobs. It has to figure out what the actual audio level is coming out of the voice for both the left and right speakers, and then add them to the accumulators here. So what we do is basically we check if the play control is enabled on that voice. If it is not, we're basically going to have 0 for the left and right. But if it is, then we check basically if the envelope level, or we grab the envelope level from the voice's envelope. Currently, this is just hard-coded to the highest value, like I showed you guys before, because I haven't really implemented that yet. But then we take the left and right levels from the voice level registers. And what we do here is we basically multiply the envelope level by the volume's left level. But there's a tiny corner case, which is that if both of these values are 0, we actually need to output 0. If they're both non-zero, we need to multiply them and add 1. And I'm not really sure where that 1 comes from, but it's documented basically everywhere. And it's kind of common to have those little quirks in these little pieces of hardware. Although, again, I don't actually understand why that would be the case. But it's not really a problem. So we did that for the left and the right. And then, again, from there, this multiply, it takes a 4-bit value because the volume is 4 bits and the envelope level is also 4 bits. And again, this is before we've actually touched the actual sound data from the voice. We're just multiplying the left and right level by the voice's level, by the voice's volume itself, to determine the actual volume of the output, and then we're going to multiply that by the actual sample output of the voice. So this takes, again, the 4-bit volumes for left and right, multiplies them by the 4-bit envelope level, and this will give us an 8-bit value. Because, yeah, when you multiply two, n bits by m bits, you get n plus m bits as a result. Out of that 8-byte value, we only want the upper 5 bits. I believe it was the upper 5. Now that I'm seeing this, I might not have done that correctly. Hold on, let me double check in some of this documentation here. Not a huge detail that I explain it super correctly, but could explain some things, some issues that I was having. Because this is basically not supposed to overflow anywhere, just because it's all basic digital math. But I think I actually saw it do that in one game, and this might actually be why. Four-bit volume is multiplied by the 4-bit envelope value of the resulting 8 bits. Only the upper 5 bits are used as output volume. Yeah, so I don't know why I shift right 1 here. This should be shifted right 3, but it might... I'm pretty sure this is supposed to be shift right by 3. I might have been messing around with that to try and get this down. Because then we'll end up with a 5-bit value coming out of this. Daniel Collins said scroll down a bit, and then he said it says the resulting value is 13-bit, and you should use 10-bit, or the 10-bit is used for output to be more correct. Yeah, it's the upper 10 bits of let me show you here. So this is a 4-bit value. This is a 4-bit value. We're going to multiply those and get an 8-bit value. Wait a minute. I know what I did here. The shift right 1 is for getting that 11-bit value down to 10 bits. It's this right here, this stuff, that needs to actually shift right by 3. Need to remember in which order that happened, and I don't think that was in this documentation. I'm going to be back in 2 seconds. All right, I'm back. Excuse me. All right, I'm back. Just looking through some other docs that should at least give me the order in which to apply these. Unfortunately, it's not documentation that I'm comfortable distributing. Which happens in emulation, unfortunately. Here come the kappas. This will take me like 2 seconds. Well, more like 10, but... Okay. So what I'm hearing in another source is that we need to do the upper 5 bits and then add 1. So I think it was here where I need to... Yeah. This is good that I went through this then because... yeah. Somehow some error was introduced. I'm pretty sure I had all these shifts in there in the first place, but for a long time I had just like silence and then a couple blips kind of coming out of this thing. And now I understand why. And I can get to that in a minute, but yeah. Anyway, so that then covers, yeah, basically this. Only upper 5 bits are used. And then, yeah, 1 is added to. So that's actually also consistent with this logic, which is good. That should make sense. Although, of course, our output is going to be a bit quieter. But I think I need to basically shift some of those values up later just to compensate for that anyway. So, yeah, so that's what this is doing, is it's basically taking these... We get the actual level, where we multiply this 4-bit value by this 4-bit value. We take the upper 5 bits and add 1 to it. And then I think that gives us a... That ends up giving us a 5-bit value. I think there are cases where that could actually be 6, but it's supposed to be a 5-bit value. After that, we'll get the actual voice output, and this is the actual sound data coming from the voice. So if this is like from a waveform or from the noise generator, there's going to be 6 bits of that. So we take the 5 bits, 5-bit level by the 6-bit data, and we get an 11-bit value. Then we want the upper 10 bits, which is why I shift right by 1 here. And that's our output for the voice. Those, once they're all mixed together, that will give us a 13-bit result, I believe it says here. Yeah, the 10-bit values for all samples are added together. Of the resulting 13-bit value, only the upper 10 are used as output. And so then that's why I mask off these lower bits here. Now, again, because we just shifted this right by 3, I think this stuff's actually going to be a little quieter. But it should actually be more correct. But also because that gives us a 13-bit value, and we're going to be outputting to a 16-bit value, I'm actually quite comfortable in just at least shifting this left by 2. Should be able to do it by 3, but I don't want it to corrupt the sign bit right now because I'm not doing any compensation for the DC offset. I'm just going to add these couple shifts in here and then run the emulator really quick just to see if we're still ballpark here. Should be. Again, I just got to click through a couple menus and just let it sit for a second. Because this is, I mean, it's basically running as fast as it should be, like 1 to 1. So like as long as we wait should be how much seconds of audio, or how much, yeah, audio will actually be produced. So we just got to sit for that. Again, like Daniel Collin mentioned last time, warp mode would be really useful here, but not going to worry too much about it. Anyway, the point there again is that this is really kind of simple, like shifting and adding and just bit mixing to actually, yeah, do the digital mixing itself. As long as nothing is too terribly wrong here, everything should be in the ranges we expect. And yeah, comments that I smell exploding headphones. Yeah, in order to not risk that, I'm going to open it in Ableton. Because I totally had some of those moments yesterday, which are adorable when you're on your own and just annoying when you're on stream. So it looks like the output is a little quieter like we expected. Yeah, to my ears, this actually sounds better. At least more correct. And I'm wondering if just because the different bits got masked out now. Which is good. So this is still more or less correct as far as we know. Yeah, cool. Also really like this music. I believe the person who did the music was the same person behind the Metroid series, which is kind of nuts. I don't remember this person's name. Also, again, I think it's super funny that there's just this DC offset here that's supposed to be a vocal sample, but yeah, I'm sure it's the modulation that'll actually fix that. Just because I implemented the noise now, and that didn't fix it, so it's the only thing left. At least in terms of generation of sound. Pedroia, how's it going? Yeah, working on the audio unit of the Virtual Boy, and that's the current sound output, so that's why we're listening to that. All comments is the shape of those waveforms. Yeah, they're pretty chunky, quite digital. So then I want to talk about basically the sound output itself. So basically the output is sampled on the sample clock, but it may actually change like on different clocks, and that's basically just because when you look at the documentation, it's like this is like a 5 megahertz oscillator that's been divided by some number. So I wanted to actually have that kind of update in the sampling itself separate because I thought that would make more sense, and I'm pretty sure that's correct as well. There are certain like waveform cycles that just wouldn't make sense based on the sample clock, but they make sense on some other oscillator, which of course will alias really badly on the system, but the docs also tell you to avoid that, so it all makes sense. So the just like we had, this single cycle advancement here, the voices also have that as well. So I'll talk about the standard voices first, because those are the ones that are basically pitching data from the wave tables. And yeah, it's just a bit simpler to keep in your head. Pedro says, are you implementing cycle correct, or are you doing real-time compilation, or are you doing that hybrid thing you talked about? I'm not really sure what you mean in that context, but I think you're actually talking about the CPU. And in this case, it's not cycle correct because it's 20 megahertz, so it's not going to be as necessary. And there's also a cache that I haven't implemented, and there's a couple things with some bus weights I haven't implemented, so it's not cycle accurate in that case. But it's quite accurate. It's pretty close. That stuff starts to matter a lot less when you get to faster CPUs like this. For these standard voices, we can just go to the cycle function here. Here we can see it's basically that same counter. So what this is basically doing is it has so each of these like standard ones indexed into these wave tables, and for these wave tables, there's 5 tables, and each has 32 samples in it. Now, last time on the stream, we were doing some math because the math didn't like look right. Like they're only 6-bit samples, so they actually need 1 byte of storage, or actually just 6 bits if that's what your memory looks like. And in this case, that is actually the case. So we only need 1 byte per, like 32 bytes per wavetable, if that makes sense. But of course, the memory mapping is gives you 4 times that size. So as it turns out, just like how all the registers in the sound unit are 4 bytes apart, it's the same way with how the wavetable memory is addressed. So it is actually, I am Cedric, thanks for the follow. So it is actually like just 32 samples, and they're mono, but they're just 4 bytes apart. So that's why we have 4 times the address space that we needed. In fact, if we go to the memory mapping, you can see that here. I just take the address minus start divided by 4 plus some offset for the different wavetables. This is actually where I messed up before, is I didn't, when I was doing this relative addressing inside the wavetables, I had it so that I could take, the address minus the like base address of that wavetable. The problem is that if you just do that and then don't add back some of the offset here, you'll get all of the wavetables actually indexing into the first wavetable. And the problem is then that you only hear intermittent sounds because a lot of the games will like clear all the other waveforms that they're not using, for example. And if they all share the same data, you'll get a lot of these cleared a lot of the time. So that was a bug that actually took me a while to track down, even though it was very simple to fix and quite obvious. So it's just happens. Yeah. So basically, then the way that the standard voices work is they have a frequency clock, which is basically like there's this low and high frequency registers, and together those form a 11-bit value. So that's 0 to 2047, and you basically take a I think it was 5 megahertz clock, and you divide it by that clock frequency, and what you get is 1/32 of the actual output of the voice. Now that sounds a bit complicated, but the math ends up being really simple. You basically just divide the 5 megahertz clock by whatever the number is in those registers. So the way we do that is we just have this frequency clock counter, which again is in nanoseconds, and this counts up by the CPU cycle period every cycle. And when that's greater than or equal to this frequency clock period, which is literally just a 5 megahertz clock, what we do is we have a frequency counter, and we count that counter up to the value specified in the frequency registers. So this is kind of like a two-stage divider, right? So we take this first stage, divides the 20 megahertz clock to a 5 megahertz clock, and the second stage will divide that 5 megahertz clock by whatever value is in these registers. Although it's, of course, 2048 minus that value, and that's just a detail of how it worked. The interesting thing about this is that it sounds like then this frequency would actually be all over the place in terms of these samples, and it kind of would be, but you would compensate for that in software. Like you'd have a lookup table to say, okay, if I have a C#6, that's going to be this particular frequency value, which ends up mapping to the right period. So it does make sense. And again, in a hardware perspective, this is basically exactly how you'd implement it, is you'd have these kind of counters that are basically just dividing this frequency, and that keeps things really simple. And of course, a 5 megahertz clock with this kind of divisor can actually get you some like wildly high values. But yeah. But this actually gives you the frequency, the frequency of the note divided by 32. And the reason that is because basically whenever this clock ticks, we update the phase of the oscillator, if that makes sense. So if you can imagine the wavetable being, 32 samples, we have a pointer into that just increments whenever this clock ticks. And because that's 32, after 32 of those it'll wrap around, that's where we get the divided by 32. Does that make sense? It might be a little bit confusing, but I mean, it basically is just like we have this two-stage clock divider that then increments another counter, and like it ends up just totally working. So that's that's really all it is. So yeah. So again, all this does with this frequency counter then is just updates the phase here, and then the output for that then, given the wavetables of the actual sound unit, we just literally look up based on the actual waveform, how that's specified. We take that times the number of slots in our wavetables. That will index into the wavetable array. We also add the phase here again, which is the offset within that. And that's it. So that's actually the entire output for the standard voices. And again, this is before all of the volume mixing, right? This is just the 6-bit output from the voices that then gets volume mixed just like all the other voices. So what made me really happy about this is it was one of those things that I just sat there kind of staring at, because one piece of documentation actually had all these tables where it was like, there's basically a 5 megahertz clock, and that has a certain period, and then here's the math to figure out like what your note frequency would be given a value, given a frequency register value, and it had a bunch of these tables, and you like look at the tables and you're like, that is just a simple clock divider. And whenever you see a clock divider in hardware, it's probably just a little counter like this. So this ends up being a really simple way to implement this. And it would have also been simple in hardware again, just because it would have just been a couple counters. And you take a bit out of one of those counters, and that ends up being a clock for another stage and stuff like that. So I think it's really interesting just how simple this is and how like easily those bits fit together, because that's literally all this took to get all the pitching that we needed for the samples. There's no other lookup tables, no nothing. This is just like super straightforward. So I thought that was pretty cool. The noise voice is also like really similar. It also has its own frequency clock counter and frequency counter, which again is that sort of two-stage divider. But then instead of updating a phase to look up in a wavetable, first of all, the like frequency divider stuff has a bit of a different phase because I think it's a 500 kilohertz oscillator that it divides down. And then instead of reading data from 32 slots in wavetables, what this ends up doing is it has what's called a linear feedback shift register, which is a really fancy term for saying like it does some bit meddling and some shifting, and will give you a 1-bit output. So if we look at most of this register is the same, except there's a couple controls for how it actually does the feedback stuff, which is sort of baked into the envelope control register. So we kind of just read that out here. So the cycle for that is, again, really simple. We have this this two-stage divider here. So we take the noise clock period, which is the 500 kilohertz clock. And whenever that fires, then we're going to do the second stage divider, which looks exactly the same as that other one did. Of course, this is dividing a different base frequency. Once we have that, then we actually do our shift register. So our shift register just basically starts with some seed value. In this case, it's known to be all ones, and it's a 15-bit wide register. So what we do out of that is, based on that register, we'd use some manipulation with the bits, and then that will give us a new value, a new 15-bit value for the shift register, and it will also give us a 1-bit output. Now, the 1-bit output ends up being used basically exactly for the sound output. So in this case, the noise generator is basically a 1-bit, has a 1-bit output. It's either full off or full on. And because that produces this feedback loop and it does some janky bit stuff, we actually get something that sounds like noise. So in particular, the actual algorithm is that we take the bits in the register, and we take one of the bits we always take every time, and then we take, based on another register, we'll take another bit in that register, right? And with those two bits, what we'll do is we'll exclusive OR those together. Then we'll take the whole register and shift it, and we'll just put this in that other slot, right? So it literally is just like moving the bits around a little bit in a deterministic way, and in a way that gives you sort of periodic colored noise. And so that's exactly what this is doing here. In particular, this noise control register determines which bit we're going to mix with bit 7, because that's just how it is in the hardware. Like, you just would have arbitrarily chosen these bits. And this bit select here will select these different bits based on, I guess, decent sounding noise colors. So for example, if you specify 3 in that register, it's going to mix bit 7 and bit 4, and then do the shifting and all the other stuff. If you select 5, it's going to mix bit 6 and bit 7 of that shift register. And again, all it does is it just reads those bits and puts them together, shifts the register, and in the new slot that was created by the shift, puts that new value in there. So that's just kind of how that feedback loop works. And then, so that's this here. We take the left bit, which is bit 7, the right bit, which is determined by this index. Then we exclusive OR those together. And then update the shift register with that new bit. In this case, it shifts left. I also need to mask this, by the way, although I don't think it matters because I'm not using any of the other bits, so it should actually be fine. Yeah, it actually will be fine. So I'm not going to do it. Actually, I will do it for clarity. Just want to shift out the other bits that are there. So I think I need, it's a 14 or 15-bit register. So it's going to be 7FFF. And then, it also turns out that we also take the opposite of whatever bit we got, and actually that ends up determining the output. But again, that's just a small detail. This is stuff that, again, is like, it's documented in the right documentation, and you just kind of have to know about it. But the overall algorithm is still literally this simple. And then here you can see I'm just, basically scaling the value, because if it's on, it's full on. If it's off, it's off. And again, like, that is literally the noise generator, right? And then, so everything else that you hear, like all of the, dynamic noises, is just changing these registers at different times. And the next step for this, of course, is to implement things like the envelope, which is going to adjust the actual volume level of the sound over time. And then, of course, there's the modulation and sweep parameters of the fifth voice, which I don't actually understand yet, but I'm pretty sure they're going to end up also being like these sort of simple counters and shifts. But yeah, I just found this really fascinating because it was so simple to actually get this to work. And it was really cool to kind of bring a little bit of hardware insight that I gained from just doing some like basic level Verilog like a year and a half ago. As soon as you know how a clock divider is implemented, then like so much of this stuff just makes sense. And I was really happy to just kind of see all of that in action. And it makes sense too, because like this would have been some relatively cheap ASIC stuff in the 90s, right? So they would have designed this. And yeah, it's just pretty cool. Zama UK 83 says, would the mass not be 7F for a 15-bit register? I believe 7F gives you a 7-bit register. This should be 15. I think 7F is 7 bits. But yeah, so that's actually all I wanted to talk about on the stream. I was just really excited again by just how I found it really cool just how simple this was. And it actually totally makes me want to get an FPGA and just make like or get my FPGA that's still in the States. And just make a little sound chip that you could drive over like I2C from a Raspberry Pi or something. Creekbot says, in the end, it's just a bunch of nans. Yeah. I literally said that to someone like 2 days ago over beer. They were saying, all you need is AND gates and OR gates. And I said, actually. Oh, that's funny. Yeah, I just really liked how simple that was from a hardware perspective, and just how easy this was to implement. Still, of course, in terms of like emulator for the audio, right now it's still dumping to wave, and that kind of sucks. Gonna want it to be. I'm just gonna generate some other audio, by the way, but actually I'll generate the Wario Land one that was clipping earlier. See if that still clips. I just found it interesting how simple it was. It was really cool. Thrash Rage T, how's it going? Oh, whoops, it didn't work. But yeah, we'll need to do like proper audio output rather than just to wave. Although even having the wave dump is nice. The other thing too is about that weird sample rate. That would actually, it's not a big deal in this case because we're like dumping out the audio separately. And even if we were generating audio along with this, you know, we would use the audio as a time source. So my guess is that the game would actually play a tiny, like very small fraction of a second faster than it actually normally would on the real system, because we'd be generating off of this sample rate that's actually a tiny bit higher than the actual system should be. But we need an integral sample rate to generate, so we need to kind of work around that. Anyway, I mean, that would be fine because the emulation time would also be slightly accelerated, so it would actually work out. Like if you wanted to compare stuff for speedruns or something, at least the in-game time would be correct, but it wouldn't be in real-world time. Anyway, there's a lot of that stuff that still needs to be solved in this emulator, but just going with this wave dump ended up also being a good choice. I really like those kind of decisions where it's just like, let's defer a lot of the routing and stuff and just focus on the logic, and we'll solve that problem in isolation. And then once it works, we actually know exactly what it needs, and then we can do the rest of the bootstrapping stuff later. This emulator has been a good example of doing that a lot, I think, like with the debugger in the beginning, and now this wave output for the audio stuff, and I've just found that to be really helpful. So I'm just gonna let this run a little bit more, and then we can hear how it sounds. And then I'm probably just gonna go turn off the stream and make dinner. But again, I wanted to just show how this was going before the next stream and before I got too much further, because I was so excited about it. Really like when stuff ends up being really simple like that. Also, again, like you can totally hear the lack of envelopes when it plays these little sounds here. Ashmedai says shared hacking discovery is the best hacking discovery. I totally agree. Like that's totally like, so someone on Reddit actually recently asked if I was doing a blog series like while doing this emulator stuff. And the reason this person asked was totally valid, because they're like, if I'm going to read all this and digest it all at once, it's way easier to do that with like a large block of text that then you can kind of break up and also go back and update and stuff. But I mean, it kind of made me think about, like, first of all, I'm not doing that kind of blog stuff because that's not really what I want to make. I want to make streams and I want to make, video content. It kind of made me think though about like, here, I'll play the music under this. It kind of made me think about like my motivations for doing this stuff. And I just realized like the reason why I kind of do these streams and why I find them really fulfilling to do rather than just like blog posts is because you actually get interaction. And like, I don't know, that makes it way more fun for me to produce, at least. And it seems like, the core of you guys that keep coming back all the time, which I really appreciate, by the way. It's really cool. It seems like that's the same reason why you guys like to watch it. It's because it is, a social thing. Also, no more clipping, it looks like. I mean, it's just random video game noises, but the panning's cool. Especially with the noise stuff, the noise is always sustained too long, and that's just like lack of envelope. Ratchet2497, how's it going? This game just sounds like a mess. And I'm pretty sure that's just because of lack of envelopes. I'm pretty sure like none of these sounds are supposed to last as long as they do. Yeah. But yeah, it's really cool to see this come together. And I think a lot of sound chips actually are, at least when you're doing these retro systems, like they are more or less this simple. Except, there's of course the stuff where there's actually analog oscillators and stuff like the SID chip and other ones that are a little bit more difficult. But a lot of them are just like, yeah, counters and shift registers. Ratchet2497 doing pretty good. Took a break with trying to figure out tile-based collisions for now. How about you? I'm doing really good. Figured out a lot of sound stuff that I'm pretty happy about. But yeah, basically it. So, again, I'm still pretty happy about doing this whole streaming thing every Thursday, so I'll probably stream again then. Unfortunately for you, Ratchet2497, I'm about to probably close the stream and go have me some dinner. Anyway, again, just thought I would share this because I thought this was really cool. And I guess if you guys have any questions, I can dig into it now. Otherwise, I'll see you guys on Thursday. Or sooner if I feel like it, apparently. But probably Thursday. And by then, I'll probably have... I'll probably do some of the envelope stuff. I'm guessing it'll be just as simple as the rest of this stuff. And then maybe the modulation and sweep stuff on Voice 5 as well. After that, there's still some top-level stuff I want to do this emulator, and there's still a couple bugs, and also a couple CPU features. But we'll see how far I get with that stuff. Ratchet2497, did I join at the end of the stream? Yeah. Sorry, man. Just a quick one today. Ursharam, it was a short stream. Yeah, it was. I consider these ones that aren't on the scheduled time just like, whatever. Just gonna do something. Creekbot says, good progress. Thanks. See you on Thursday. Thanks, man. Ratchet2497. So again, I am streaming now every Thursday at 8 p.m. CET. So if that works for you, then yeah, might be easier to catch me then. XMHG says, what's for dinner? I'll probably make tacos. Ernest, nice to see the emulator coming along. I've got a quick question. Sorry if you've answered already, but what's an envelope? Yeah, that's actually a really good question that I didn't explain. An envelope, at least in audio context, is usually just like basically a volume ramp. For example, I'll pull up the sort of quintessential one, which is called an ADSR envelope. This is the reason why I didn't explain this is because this is like really... This is really basic DSP stuff, which is totally stuff I just forget to explain. So I apologize for that. So for example, here's what an ADSR envelope looks like. Let me see if I can bump the size up here. And what this represents is if you have a sound playing, you want to like fade it in and out over time. If you just like start the sound at full volume and then stop it, go to silence, you'll get these little clicks when the sound starts and stops. And that's because the sudden change in volume actually introduces some high frequency stuff. Because yeah, totally moving air. So anyway, this is like your sort of typical quintessential envelope where you have attack here, which is how long the sound will take to get from no volume to full volume when you like hit a key. Decay is where then it will ramp down to the sustained volume. So like attack, decay, and release are all in the specified in the time domain. Sustain is actually in the like output domain. So like when you hit a note and you hold a note with your finger, it will go through this and it will hold here until you let go, and then it will release, and then it will just ramp back down to 0. So this is Osmodice says, I remember such ADSR graph from way back in my Commodore 64 manual. Yeah, the SID chip in the 64 had great envelopes. This sound chip does not. This sound chip just does like some, basically, I think it has like a reset value, and then it has like an interval value, and then it has like whether or not it's ramping up or down. So it seems like in that sense, it would actually be a little more flexible because you could do more things with it than just this kind of curve. But I think this kind of curve works and it's kind of proven to be really comfortable for musicians. So I'm not sure if it was the best hardware choice, but it was simple to implement, I'm sure. So probably makes a lot of sense. Anyway, that's what an envelope kind of usually looks like. And an envelope, again, that like the point is just to, instead of having a sound just be like a Boolean on or off, like you can actually fade it in and out to reduce those sort of clicks that happen at the beginning and end of sounds. So that's also why I say like if it like when that Wario game just sounds like a complete mess because the sounds are like lasting way too long, that's why I think that's envelopes. It's because they should have just like faded out and then stopped playing. So that should fix that. And in terms of modulation and sweep, which are the other terms that I probably didn't explain, those could really mean anything depending on the sound chip, depending on who you're talking to. But in this case, I think modulation just means changing the frequency of the oscillator just based on some table of values, and the sweep is basically doing the same thing, but instead of changing the frequency, it'll change. Or sorry. I think the sweep also actually operates on the frequency, but it will sort of have ramps, kind of like the envelope circuit will as well. Again, I'm not actually sure because I need to look in the documentation some more, but I'm sure it'll be pretty simple stuff. Osmodice says, interesting how much of this stuff was just normal to learn with the old simple computers. That is actually pretty interesting. But I mean, then you were actually touching the hardware, so I guess it kind of makes sense. And if you've ever worked with like any MIDI anything, you also probably would have learned this. So I wonder if that was actually kind of wise that they wanted to sell these computers as things you could do anything with. So you wanted to do music. Here's how you do music. Anyway, pretty cool. So I'm gonna head out. Thank you guys for joining me for a tiny quick stream on such very short notice. Really appreciate that, and I'll have this uploaded pretty quick. But yeah, I'll see you guys again on Thursday.